My name is Masoud Mohseni. I'm the head of quantum team at Hewlett-Packard Labs. I'm very happy and excited to be here at Supercomputing 24 to represent Hewlett-Packard Labs. We have actually an exciting news that we have published a paper on how to build a quantum supercomputer, discussing scaling challenges and opportunities. And in this paper, we discuss various technical and fundamental challenges to build a scalable quantum computer, starting from hundreds of qubits all the way to millions of qubits, discussing what are the roadblocks, what are the things that are stopping us from building larger systems. Basically, the idea of quantum computing has been around for 40 years. It started as an intellectual curiosity in 80s, and then we are discussing possibility of having a potentially realizable technology, and people are asking if this is such a promising venue, why we don't have an operating quantum computer yet. And so in this work, we address all the challenges that are known today, and some of them are being overlooked or underappreciated, and we trying to put it in one place. Some of them are mentioned in a piecemeal fashion elsewhere, but it was never discussed in one place. So we are providing a comprehensive list of these challenges and providing research and development opportunities to address them. And so that includes from qubit quality, wafer scaling, quantum control, calibration, real-time error correction, distributed hybrid quantum classical co-processing, and user-friendly APIs for people who are interested to prototype and explore quantum algorithm to be able to have access to various different hardware in a heterogeneous fashion. So the idea is that we are able to run various different SDKs for various different quantum processors in a seamless fashion from a single API. And we have in 6 different layers, we have HPC integration inside a quantum computer as well as outside to connect them. As part of this, we discovered a new framework for distributed quantum computing, which we call it adaptive secret knitting, which we break down a large quantum problem into sub-parts or sub-problems that we can distribute it to various different quantum computers. The reason we need to do this is that these current noisy intermediate quantum devices that are called NISQ are not going to scale beyond 1,000 qubits, maybe a few hundred. That might be the maximum size. And once we do error correction, the number of logical qubits are going to be small as well. So for foreseeable future, we need to work with a small size quantum processor. And the industry scale problems are much bigger. So you have to distribute this over various different processors. So we designed this quantum workload hypervisor, which basically invokes this adaptive secret knitting. And it just cut a quantum secret into patches. This is the secret cutting, and then it can knit them, basically combine the solutions to build the global picture that you wanted to simulate at the beginning. This was proposed earlier with some classical post-processing overhead, which is exponential. So here we actually we have an algorithm to have a peek at the entanglement heat map, so you can see where are the places that the entanglement is minimal. So once you do the cut there, you can potentially merge the solution with the polynomial overhead. So the sampling overhead becomes tractable for interesting problems that they have quantum correlations on the order of maybe hundreds of variables, but there is not significant correlations on the thousands of variables. So you can basically do a distributed quantum computing this way. There are many other elements in this paper that we discussed. It's basically a full roadmap for building a scalable system, but we listing the challenges that we are aware of today to our best of knowledge. We are not necessarily claiming that we have solutions to all these challenges. We want to share that with the community so other people can contribute and basically potentially provide solutions to these challenges. So we encourage people in quantum computing community to contribute to this collaborative efforts, and hopefully we can shed light on these obstacles and provide venues for research and development to tackle them.